Working 8.7, picking up where I left off here at number 11. Now we're going to shift our attention now to Taylor series instead of Maclaurin series. Now the only difference between a Taylor series and Maclaurin series is that instead of centering our series at a equals 0, we're no longer going to do this. We're going to just center it at whatever they give us. So let's look at f of x is equal to x to the 4th minus 3x squared plus 1. And it's going to be centered at a equals 1. So this is a finite polynomial function. And they're giving you this example just as a warm-up, just to kind of get you to see how things are going to work. Assuming that this has a power series expansion, we know we can rewrite it as a sum n equals 0 to infinity c sub n x minus a to the n. In this particular case, a is going to be 1. So this should be able to be written like this. But we've got to figure out what our c sub n's are. So our c sub n's, the formula we have is it's the nth derivative at a over n factorial. Now in the past, the a has always been 0, and it's been pretty easy for us to plug in that number and get our c sub n. So let's just see as we move through these problems how using something other than 0 is going to affect how we actually come up with those c sub n's. So I will start off by trying to make a list of my derivatives. So first of all, the 0th derivative of this function is the function itself. And when I plug 1 into this, so notice I'm plugging in 1 instead of 0, I get, let's see, 1 minus 3 plus 1, right? So that's negative 1. And then I take the first derivative. So the first derivative of this function is 4x cubed minus 6x. And when I take that first derivative and I plug in 1, I get 4 minus 6, which is negative 2. And then when I plug in the second derivative, I get 12x squared minus 6. And when I plug into the second derivative the value of 1, I get 6 out. And let's see what happens as I continue this. The third derivative is going to be 24x, and then that's it. So the third derivative at 1 is going to be 24. And you can see, because this is a polynomial function, as I take the derivatives, it keeps on getting nicer and nicer. Finally, the fourth derivative is just 24. And if I plug 1 into that, nothing happens. I get 24. And now the rest of the derivatives, every one of them from here on out is 0. And that means that this c sub n that we get, which is the nth derivative at 1 over n factorial, this is going to be equal to 0 over n factorial as long as n is, let's see, the fifth derivative and on, greater than or equal to 5. So that means I'm just going to have a bunch of zeros once I get to the fifth power in my power series. So it's time for me to write out my power series. I'm going to keep those right there. This function can be written as, I guess my voice is never going to clear up this semester. So I'm going c sub 0, right? C sub 0 is the 0th derivative at a, which is negative 1, over 0 factorial x to the 0, plus, now c sub 1 is going to be the first derivative at 1, which is negative 2, over 1 factorial x to the first, sorry, I messed up. It's not x to the 0, it's x minus a to the 0 plus then negative 2 over 1 factorial, then x minus 1 to the first power. See, it's not a Maclaurin series, so these powers here are going to have to be on the binomial x minus a, not just x. And then I have plus, let's see, I'm letting n be 2 now, so I'm in my second derivative at 1, which is 6. Over 2 factorial, and then x minus 1 to the second. Plus, now I'm at my third derivative, so 24 over 3 factorial, x minus 1 to the third. And then I have one more, because everything after this is 0. So 24 again over 4 factorial, x minus 1 to the fourth plus, and then like I said, just zeros from here on out. So I don't really even need those. So I actually get a finite series. This is not an infinite series. It doesn't keep going forever, which kind of makes sense if you think about it. We're trying to approximate a polynomial function with a polynomial function. So, I mean, we're trying to approximate a polynomial function which is powers of x with the sum of powers of x. So it should be finite. All right, let's see what we get here. This is 1, right? Anything to 0 is 1. Negative 1 over 0 factorial is 1, so we should just get negative 1 here. Plus, let's see, negative 2 over 1 factorial is negative 2, and then times x minus 1. So I'm just going to put negative 2 times x minus 1. And then over here, the bottom is just 2, and 6 divided by 2 is 3, so we get 3 x minus 1 squared. And then over here, remember 3 factorial is 3 times 2 times 1, so that's really a 6. And 6 goes into 24 8 times, so 8. Then x minus 1 cubed. And then plus, let's see, 4 factorial, 4 times 3 times 2 times 1. We said this was 6. 6 times 4 is 24, so that's just going to be 1. So that's just x minus 1 to the fourth. And that is our Taylor series. Why didn't I? 3, 6, 8, 3. Where's that one coming from? Oh, I see. It's my first problem. Cut me some slack here. This is not 8. That's 4. Okay, this was 6. 24 divided by 6 is 4. I did 24 divided by 3, which is 8, but it's 3 factorial. All right, well, got to get warmed up here, okay? Let's move on to number 12. All right, for 12, f of x is x minus x cubed. We're going to do this about a equals negative 2. A equals negative 2. So again, I'm going to need to start taking derivatives to come up with my c sub n's. So the 0th derivative of this function is just the function itself. Now what I need to do is look at the 0th derivative at negative 2. So when I plug in negative 2, I get negative 2 minus negative 2 cubed. That's, this right here is negative 8, but then I'm subtracting it, so positive 8. So this is a 6. And then I take the first derivative, which is 1 minus 3x squared. Then I look at the first derivative at -2. So I get 1 minus 3 times -2 squared. -2 squared is 4, times 3 is 12. 1 minus 12 is -11. And this is going to do exactly what the previous one did. Eventually I'm going to get zeros here, which is going to be nice. But this is just -6x. And when I plug into the second derivative, -2, I get positive 12. And then my third derivative is going to be -6. And so when I take the third derivative and I plug in -2, doesn't matter, I still get -6. And then from here on out, when I take derivatives, these are all going to be zeros. So it won't matter. So here are the C sub n's, or a part of what I'm going to get my C sub n's from with these numbers, but then after a certain point, I'm not going to have them. So C sub n will equal the nth derivative at -2 over n factorial. That's going to be equal to 0 over n factorial, which is 0, as long as n is greater than or equal to, let's see, 4 here is where it starts. So I'm only going to have C sub 0, C sub 1, C sub 2, C sub 3, and that's it. I'm not going to have anything after that. So let's go ahead and write down the power series here. I'll leave these numbers here so I can refer to them in a minute. So this should be equal to this function. The Taylor series of this, about this, is going to be C sub 0, which will be this number, 6, over 0 factorial, x minus a to the 0. Now, this is going to be x plus 2, so I'm just going to change it now. And then plus, now it's going to be this one, which will be -11 over 1 factorial and x plus 2 to the first power. And then plus this number, which is 12, over 2 factorial, x plus 2 squared, and then one more, -6 over 3 factorial, and then x plus 2 to the third, and then it will be zeros the rest of the way. So I'm not going to worry about those. And now I'm going to clean this up. 6 over 1 is just 6, and then this right here to the 0 is 1, so I just get 6. And then -11 over 1 factorial is -11, x plus 2. And then let's see, 12 divided by 2 factorial is 2, so that's 6, x plus 2 squared. And then -6, remember 3 factorial is 6, so this is going to be -1, x plus 2 cubed. So that is the Taylor series for that function about a is -2. So, I mean, what is this thing? I mean, what does this represent? Let me do something here. I'm done, but let me show you something. Okay, so I'm putting distributing. Here I'm going to square this. X squared plus 4x plus 4. Still have to distribute -6 through minus. I'm going to expand this out. It should be x cubed plus 6x squared plus, let's see if I get this right, 12x plus 8. Pretty sure that's what it is. And then I get, let me try and clean up a little more. Distributing here this 6 through. Distributing the negative through. And let me collect like terms together, and I'll put it in, I guess it doesn't matter what order I put it in. Okay, how about numbers? How about numbers? 6 minus 22 plus 24 minus 8. So what is that? 6 take away 22 is -16. If I add 24 to that, I get 8. and then subtract 8, it's gone, so I don't have anything. These are gone. All the constants are basically gone. Now let's look at my x's. I have, where are my x's? Okay, I've got negative 11x and 24x. So that's going to be 13x. And then take away 12x, that just leaves me 1x. And then let's look at my x squared. 6x squared and negative 6x squared, they're gone. And then my x cubed, I have minus x cubed, that's all I have, minus x cubed. Oh, whoa, whoa, wait, hold on. That's the original function. Look at that. So what we've said is that if you want to approximate this function near negative 2, centered at negative 2, so imagine that graph around negative 2, what should I use to approximate it? I should use this, but it turns out that this is actually the same function. Does that make sense? If we're trying to estimate a finite polynomial with a power series, which is again it's a polynomial, then it makes sense that what we should estimate it with would be the polynomial itself. So this only happens when these are polynomials. If this is a polynomial, our best estimate of a polynomial is the polynomial itself. It's kind of amazing though that we can get that from all that work we did. Now, we would never really try and do a power series or a Taylor series or even a Maclaurin series for a polynomial. These first two examples were just to get us used to what we're doing and to kind of show you that, look, the result makes kind of sense. We're estimating a polynomial with a polynomial. 13, though, we have natural log x. And we are going to be looking at this centered at a is 2. All right. Now these derivatives are going to start to get kind of funky. So I think what I'll do is this. I'm going to move this over a little bit. F of x is natural log x, a is 2. So let's start looking at our derivatives. The zeroth derivative is natural log x. If I take the zeroth derivative and I plug in 2, I get natural log 2, which is just a number, whatever it is. Now, the first derivative is 1 over x, which is the same as x to the negative 1. Now, I'm doing that because I'm going to take the derivative again in a second. It's easier to take derivative of this than this. So f prime, the first derivative at 2, you're going to plug 2 into this, you get 1/2. Now we take the second derivative. The second derivative, what happens here? The negative 1 comes out, so I get negative 1 x to the negative 2, which remember, that's just negative 1 over x squared. So when I take the second derivative and I plug in 2, I have negative 1 over 2 squared. So I'm going to write that as 4. Now I take the derivative again. The third derivative, the negative 2 comes out and it becomes positive 2. And now x to the negative 3, which is 2 over x cubed, which when I plug 2 into that, I get 2 over 2 cubed, which is 8. Now I know I can reduce that, but because of a pattern we're trying to see here, I'm going to just leave it as is. Fourth derivative of this, the negative 3 comes out, I get negative 2 times 3x to the negative 4. Now, I agree that this is a negative 6, but again, I'm going to leave it out, negative 2 times 3 over x to the 4th, because I'm trying to get us to see a pattern here. If we plug into the fourth derivative the value of 2, we get negative 2 times 3 over 2 to the 4th power, which is 16. So let's try and figure out what's happening here. Well, let me do one more. 5th derivative at x. So the negative 4 comes out here, it becomes a positive. I now have 2 times 3 times 4, x to the negative 5, which is going to be 2 times 3 times 4 over x to the 5th. And when I plug in 2, I get 2 times 3 times 4 over 32. All right, so let's work backwards. We have this right here is 4 factorial. This one up here is 3 factorial, but it's negative. This is 2 factorial, but it's positive. This is 1 factorial, but it's negative. And this is 0 factorial, but it's positive. Natural log 2 doesn't belong here. It looks like it's not part of a pattern. And that's okay, we'll deal with that in a minute. But everything else looks like it's following a pattern. Also, the denominators are just powers of 2. Right? This is 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 squared, 2 to the 1st. So it looks like this number here, the derivative I'm at, right? This on the bottom is going to be 2 to that derivative. The top is going to be this number minus 1 factorial. So this would be like 5 minus 1 factorial. But then I also have the sign switching. You know, positive, this one before was negative. But it would follow the same pattern. We would have on the bottom 2 to the 4th, because this is a 4. And then this up here should be 4 minus 1 factorial. Now the negative, I'll deal with it, okay? I'll deal with that when I start to write this thing out. So what would the next one be? If we did the 6th derivative, we would get a negative 2 times 3 times 4 times 5 over x to the 6th. So when we plug in 2 into this, we get negative 2 times 3 times 4 times 5 over 64. So it's you can see it's following the pattern that I just mentioned. All right, so let's try now to write out, you know, our power series, our Taylor series for this, and remembering that we're going to be using this, and a was 2 over n factorial. All right, here we go. I will get rid of all this, so I'll need some room. I'll just keep this stuff on the side. Remembering that, you know, this was the 0th derivative at 2, and then this is the 1st derivative at 2, 2nd derivative at 2, 3rd, 4th, 5th. So when I write this out, I have that this function, natural log of x, is equal to c sub 0, which is going to be this right here with 0 in there, which is that number over 0 factorial. So natural log 2 over 0 factorial, x minus 2, that's x minus a, to the 0. So that's the first term, plus c sub 1, which would be the first derivative at 2, which is 1/2, over 1 factorial, x minus 2 to the first. Then I have plus this one, negative 1/4, over 2 factorial, x minus 2 to the second. And then I'm going to get 2 over 8 over 3 factorial, x minus 2 to the third. So I'm right here, I've done those. The next one is plus negative 2 times 3 over 16 over 4 factorial, x minus 2 to the 4th. I'll do one more. Plus 2 times 3 times 4 over 32 over 5 factorial x minus 2 to the 5th plus dot dot dot. So that's my Taylor series for natural log of x about a is 2. Hey, come on in. And now I'm going to try and maybe clean this up and get a formula for this. So the first one here, this is 1, that's 1, so this is just natural log 2. We said that one didn't follow into the formula too much. And then what I'm going to do here is I'm going to clean up this fraction. This is like 2 fractions, so I can flip, so it becomes 1 over 2 times 1 factorial x minus 2 to the 1st power. This one becomes minus, because there's a negative there, 1 over 4 times 2 factorial. So again, writing that like that and flipping it. X minus 2 squared, and then plus, and then we're going to go 2 over 8 times 3 factorial, so flipping again, x minus 2 cubed, and then minus, because this one's negative, 2 times 3 over 16 times 4 factorial, x minus 2 to the 4th, and finally, if I can fit this in here, plus 2 times 3 times 4 over 32 times 5 factorial, x minus 2 to the 5th plus dot dot dot. All right, so remembering what we had earlier, we said that this one didn't follow the pattern, so I'm not going to worry about it. This number right here, this number right here, this number right here, this number right here, these were all powers of 2, right? And these were all factorials, right? But they were always going to be, there we go, those are, these factorials would be equal to the power up here, right? These factorials would be the power. And then in the numerator, this, this, and this were factorials, but they were always 1 less than the power out here. So this is 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial. So with that in mind, let me try and rewrite everything again. This is natural log 2 plus 0 factorial over, this is 2 to the 1st power times 1 factorial times x minus 2 minus, this right here is 1 factorial over 2 squared times 2 factorial x minus 2 squared plus the top here is 2 factorial over 2 cubed times 3 factorial x minus 2 cubed minus, this is 3 factorial over 2 to the 4th times 4 factorial x minus 2 to the 4th, and finally plus 4 factorial over 2 to the 5th times 5 factorial x minus 2 to the 5th. I think I'm off camera here. It's good enough. All right, so now what I'll do is I'll try and write this in sigma notation. So this should be equal to, now this didn't fall into the pattern, so I'm just going to put natural log 2 here, plus sum n equals 0 to infinity. All right, so this first one, 0 factorial. If I'm starting at n is 0, then it's going to be n factorial on top. All right. 2 to the first power. So if I'm starting at n equals 0, that needs to be 2 to the n plus 1. So when I plug in 0, I get 1 here. When I plug in 1, I'll get 2. When I plug in 2, I'll get 3. When I plug in 3, I'll get 4, and so on and so forth. Same with the factorials. This is a 1 factorial. So this is going to be n plus 1 factorial here. So when I plug in 0, I get 1 factorial here, 0 factorial here, 2 to the first power here. So that takes care of this. And then the x minus 2, the power on this needs to start at 1 and go 2, 3, 4. So I'm going to do n plus 1 there also. And that should be our Taylor series. But there's a little bit of cleaning up I can do. I can rewrite the n plus 1 factorial as n plus 1, peel off the n factorial, cancel. So we should get natural log 2 plus sum n equals 0 to infinity. I'm going to run out of room. I'll do it right here. So this is equal to natural log 2 plus sum n equals 0 to infinity. On top you have a 1. On the bottom you have 2 to the n plus 1. And then n plus 1 here. And then times x minus 2 to the n plus 1. And that is your Taylor series for natural log of x about 2. Check it real quick. Yeah, that's fine. The book answer, they switched the index here to 1. So I'll do that just to show you. This is correct. It's not wrong. It's just they want to have a different index. That's fine. So what I'm going to do is change this index to a 1. So I have to replace all my n's with n minus 1 in order to do that. So when I put n minus 1 here and add 1 to both sides, I'll get my sum to start at 1. And then 1 over, if I replace this with n minus 1, n minus 1 plus 1 is just 2 to the n. N minus 1 plus 1 is just n. And then x minus 2, same thing here, n. So I believe that's what the book shows as the answer. I forgot the alternating part. Shit. Forgot the alternating part. It had to alternate starting with the positive, right? And then go negative, positive, negative. So I'll adjust that to do that. Start at positive, I do that, right? Here, I do that. So if I plug in 0, I get a positive 1. If I plug in 1, I get negative. So that'll give me my alternating. But then when I replace that with n minus 1, it'll be that. I had a feeling I was going to forget that alternating part. Okay, that's it for that one. Yeah, just remember, it was an alternating series. So I had taken care of all this stuff and I was focusing all of my attention on that. I forgot that we alternated, so I need to start at positive, then negative, positive, negative. So this will take care of that. That'll make that happen. I don't feel like going back and redoing that whole problem, so I think hopefully you understand. You know, what's going on? I felt good today. I thought I was going to come in here and have a great session. I guess I'm just getting ready for the break. Next one, 1 over x is the function. And we're going to do it about a is equal to -3. All right, so here we go. We are going to start doing our derivatives. The 0th derivative. Remember, this is x to the -1. So the zeroth derivative is just 1 over x. X is negative 1. So when we plug in negative 3, let me just make sure it's negative 3. It is. We get, in here we get negative 1/3. Now we take the first derivative and we get negative x to the negative 2, which is negative 1 over x squared. So then when we plug into this derivative negative 3, we get negative 3. When we square it, it's going to be positive 9, so it's not going to matter. We get negative 1/9. And then when we take the second derivative, this is the negative 2 comes out, hits this, becomes positive 2. So we get 2x to the negative 3, which is going to be 2 over x cubed. So when we plug in negative 3, we get 2 over 3. Negative 3 cubed is negative 27. So far, they're all negative. Let's see, when we do the third derivative, we get negative 6. Or actually, I'm going to do what we did before, because I know where that's headed. Negative 2 times 3, x to negative 4. That's negative 2 times 3 over x to the 4th. When I plug negative 3 in there, on the top I have negative 2 times 3. On the bottom I have negative 3 to the 4th power. So that's negative 3 times negative 3 times, it's going to be positive, and it's going to be 81. But we're already noticing that all the denominators are always just powers of negative 3. So again, I have a negative number. Let's do one more. So when the negative 4 comes out, I get a positive, so 2 times 3 times 4, x to the negative 5. So this is 2 times 3 times 4 over x to the 5th. Because it's the 5th power, when I plug negative 3 in, I'm going to get a negative, because this is the 5th power. So even though the numerator is positive, the denominator is going to be negative. And then I'm just going to put here negative 3 to the 5th. All right, so what's the pattern? What's the pattern? They're all negative, right? They're all negative, so that's good. I don't have to worry about that. They're all negative. The tops looks like they're factorials. That looks like 4 factorial, and that's 4. This looks like 3 factorial, and that's a 3. That looks like 2 factorial, that's a 2. That looks like 1 factorial, that's a 1. That looks like 0 factorial. So again, forget the negative there. And then the bottoms are all just powers of 3. 3 to the 1st, 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th. And so this number 5 is always 1 more than this, right? 5, 4, 4, 3, 3, 2, 2, 1, 1, 0. So I think I can come up with a general formula for my C sub n. I think a general formula would be pretty easy to come up with here. But I'm going to put it all together and try and write the power series out. So let me write these down over here. I have negative 1 over 3. I have negative 1 over 3 squared. I have negative 2 over 3 cubed. Negative 2 times 3 over 3 to the 4th. And negative 2 times 3 times 4 over 3 to the 5th. So those are my derivatives evaluated at negative 3. 0th derivative first, derivative second, third, fourth. I'm just writing those down so I can look at them in a second here. So my Taylor series for this, 1 over x, should be equal to the 0th derivative at negative 3, which was negative 1/3, over 0 factorial, and then x minus negative 3, which is plus 3 to the 0, plus, now again, negative 1 over 3 squared over 1 factorial, and then x plus 3 to the first, and then plus negative 2 over 3 cubed over 2 factorial x plus 3 squared, and then let's see, negative 2 times 3 over 3 to the fourth over 3 factorial x plus 3 to the third. I have enough room, I can do another one, plus negative 2 times 3 times 4 over 3 to the fifth over 4 factorial x plus 3 to the fourth. So I'm wondering if I should flip again to make it easier for you to see. This is negative 1 over 3 times 0 factorial x plus 3 to the 0. And then this is going to be another minus. So minus 1 over 3 squared times 1 factorial x plus 3 to the first power minus 2 over 3 cubed times 2 factorial x plus 3 squared minus 2 times 3 over 3 to the fourth times 3 factorial x plus 3 cubed minus 2 times 3 times 4 over 3 to the fifth times 4 factorial x plus 3 to the fourth plus dot 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 plus dot dot dot. So I'm ready to write my sigma notation, but I want us to notice something that we could do right now. We said these numerators were factorials, right? This was 4 factorial, 3 factorial, 2 factorial, 1 factorial, 0 factorial. So let's rewrite those. 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, and that would continue. And do you see that they cancel with the denominator? So all we really have is this. We have a negative on every one of these. So we have a negative, sum, n equals 0 to infinity. And then this is 3 to the first power, right? And then the only other thing we have is x plus 3 to the 0 power. So I need to put 1 over 3 to the n plus 1, that'll give me 3 to the first power, and then x plus 3 to the n. So if I plug in n is 0, I get 3 to the first, and then I get x plus 3 to the 0, so that'll give me this. If n is 1, I get this, and then this, and that continues. In the negative, I could have the negative here, or I could put the negative just up in here like that, and that should do it. Let me see. Yeah, go figure. They put the negative on the outside. All right. Okay. You do? Okay. This is, let me see how much I've got into this. I'm 40, no, I've got 45 minutes onto this video.
It was pretty intense.
Which one are you working on?
8.6.
8.6? Okay, this is 8.7. So let me do one more, okay? And that'll be about an hour of video. That'll be perfect for me to upload. So let me just do one more of these, and then I'll help you out. 15. I'm pretty sure I'm doing 15 in class. F of x equals e to the 2x we're going to do that about a is 3. All right, let's start doing derivatives. So the 0th derivative of this function is itself. And if I plug in to this 3, get e to the 2 times 3, which is e to the 6. If I do the first derivative, because of chain rule, the derivative of this is itself, but then a 2 pops out, so I'm going to get 2e to the 2x. If I plug in 3 into that first derivative, I get 2e to the 6th. If I do the second derivative, same thing, another 2 pops out, so now I get a 2 squared, e to the 2x. And the second derivative with 3 plugged in will just be 2 squared times e to the 6th. And then the next time, the third derivative, this one's actually going to work out pretty clean. I'm going to get 2 cubed because another 2 pops out. And then when I do the third derivative at 3, I get 2 to the third e to the 6th. And then I keep doing this. So it looks like my c sub n's are going to be, let's see, on the first one, well, here this is 2 to the first, this is 2 to the second, 2 cubed, but this one right here I could write as 2 to the 0, e to the 6th, right? So it looks like my c sub n is going to be 2 to the n, e to the 6th. That never changes in all of them, over n factorial. But I don't even think I need to write all these out. I've got a nice clean formula for it, right? If c sub 0, 2 to the 0 is 1, e to the 6 over 0 factorial, that's this. Well, this part is this. And then this one, if c is 1, we get this, it's that. So I think we're in business. I think I'm going to just go straight to the series without writing it all out. It should be that e to the 2x is equal to the sum n equals 0 to infinity of the formula for c sub n, which is 2 to the n e to the 6th over n factorial, but then x minus a to the n. That'll do it. I'll do one more. We'll do 16. F of x sine x, a is pi over 2. So some derivatives. 0th derivative is itself. Plug into the 0th derivative, pi over 2. Sine of pi over 2 is 1. Okay, first derivative, cosine x. Plug in pi over 2 into cosine x, and you get 0. Second derivative, negative sine x. Second derivative, pi over 2. So if you do sine of pi over 2, is going to be 1, but then make it negative, so negative 1. And then third derivative, derivative of that is negative cosine x. When we plug in pi over 2, cosine pi over 2 is 0. Fourth derivative, sine x. We're back to where we were earlier. Fourth derivative, pi over 2 is 1. So what's going to happen now, because we're back to sine, is that we had 1, 0, negative 1, 0. So we're going to have 1, 0, negative 1, 0, 1, 0, negative 1, 0, and that's going to continue. So I think for this one, because I don't have a nice clean formula that I can write for the c sub n, what I'm going to do is I'm going to write out these values. I'm just going to remember 1, 0, negative 1, 0, and then it repeats 1, 0, negative 1, 0. I'm just going to write it out for sine of x. So here we go. First, we have sine x equals, all right, this number, 1, over 0 factorial, x minus pi over 2, x minus a to the 0, plus, now this number, 0, over 1 factorial, x minus pi over 2 to the first, plus, negative 1 over 2 factorial, x minus pi over 2 squared, plus 0 over 3 factorial, x minus pi over 2 cubed, plus 1 over 4 factorial, x minus pi over 2 to the fourth, plus 0 over 5 factorial, x minus pi over 2 to the fifth. Do I need to go more further? All of my odd ones are not here. And all of my even ones are there, but they're also alternating in sign. So, yeah, let me just put the next one. Next one that would be out here would have been a negative 1, and then it would have been 6 factorial, x minus pi over 2 to the sixth. So that gives me my pattern. Look, 1, 0, negative 1, 0, 1, 0, negative 1, 0, and then it would continue. So this is sine x equals, all right, this is a 1, that's a 1, so I get 1. Okay, this is minus 1 over 2 factorial, x minus pi over 2 squared. The next one I get is plus 1 over 4 factorial, x minus pi over 2 to the fourth. The next one I get is minus 1 over 6 factorial, x minus pi over 2 to the sixth. Any guesses to what the next one would be? Well, it's going to be plus, and it's going to be even. So 1 over 8 factorial, x minus pi over 2 to the eighth. And then the next one would be minus 1 over 10 factorial, x minus pi over 2 to the 10th, and then so on. So let me make sure I don't mess this one up. It's alternating, so I'm going to start my sum, n equals 0 to infinity. I need to alternate, I need to start, I believe I can get this still within my formula. So to start positive, negative, so I'm going to use negative 1 to the n. Now, all of these fractions out front are just 1 over factorial. So 1 over 2 factorial, 1 over 4 factorial, 1 over 6 factorial, 1 over 8 factorial, 1 over 10 factorial. That's 1 over an even factorial. In fact, this first one right here, this is 1 over 0 factorial. So what I'm going to do here is I'm going to put 1 over. Now I need to create just even numbers, but I need to start at 0. So how about 2n factorial? So now if I plug in 0, I get 0. When I plug in 1, I get 2. When I plug in 2, I get 4, 3, 6, 4, 8, so on and so forth. So that should take care of that blue part. And then out here, it's the x minus pi over 2. And then those are all also just even powers. So, and I want to start actually at this first one, right, this right here. So I want to start at 0. So same thing, 2n up here. And that should create the series. So that is your Taylor series expansion of sine x about the value pi over 2. Let me check it. 2 factorial negative 1 to the n, yes. All right, that's it.